I am Václav Novotný, and welcome to my tutorial of thermodynamic cycles in energy engineering. This is the second part of the tutorial for Rankine cycle with regenerative feedwater heating. After setting of the methodology in the first video, here we will calculate more sophisticated configuration of the cycle where we have 5 feedwater heaters. One open as the Deaerator and 4 of them closed. The configuration shown here utilizes so-called condensate cascading. That means that the condensate from the feedwater heater is routed downstream into the next feedwater heater at lower temperature level. This goes on until the Deaerator on the high pressure part of the cycle or into the condenser in the lower pressure part of the cycle. So, based on the methodology from the previous video, we will use the same boundary conditions and we will prepare a similar table just with respective nodes according to our process flow diagram, which means nodes 1, after pump, again isentropic point 2, then actual point 2, or for example for the turbine bleeding nodes, so we have here node 11, but we have 10, then 11 isentropic, 11 bleeding, and then 11 going to the feedwater heater. So isentropic is auxiliary, bleeding is before the pressure drop, it's actually at the outlet of the turbine, and then at the point at the inlet of the feedwater heater. On top of the provided boundary conditions and assumptions, we will have one more parameter specified for the cycle, and that will be the temperature of the feedwater going into the boiler. Here, temperature at point 8. So in our case, temperature feedwater, and we will specify that we want it at 230 degrees C. So now we can follow through the basic parameters that we know in a similar method or same method as we did before. So we have specified the pressure at the turbine inlet at 0.9. Then we have specified temperature at the turbine inlet at 0.9. And we know the cooling water inlet temperature, point CV1 here. And we know the temperature at the point 8 inlet into the boiler, which is here feedwater temperature 230 degrees C. Additionally, same as last time, we know the temperature increase of the cooling water in the condenser is 10 degrees C. So the cooling water outlet is cooling water inlet plus specified delta T cooling water. And our saturated temperature at the point 1 will be derived from this temperature by minimum temperature difference. So 30 degrees C plus minimum temperature difference at low pressure part of the cycle, 33. Now we have specified subcooling at the end of the condenser. So that's saturated temperature minus the subcooling. And from the saturated temperature we can get saturated pressure. So again, function props SI, where we want to get pressure based on temperature, which is the saturated temperature, and quality with any value between 0 and 1, and where our working fluid is water. And of course temperature needs to be in degrees Kelvin. And pressure needs to be, or all the parameters needs to be put in capital. And we want megapascals, so we divide the value by 1 million. So now we have pressure and temperature at the point 1, and from that we can obtain again other thermodynamic parameters like enthalpy, props SI, where we want enthalpy based on pressure times 1 million, then temperature plus 273.15 to get kelvins, and our working fluid is water. And again we want more we want nicer units like kilojoules per kilogram, so divided by 1000. Same function goes also for the entropy. Just we change the output parameter. Let's get more decimals. Now change to the ideal state at 2 to isentropic is so the entropy remains the same, but we still don't have but at this point we will need to get the pressure at the point 2. For this we need to specify actually the temperatures at the outlets of our feedwater heaters. We have 5 feedwater heaters, and the overall temperature that we want to heat up, the overall temperature difference, is this 230 minus 29, which is, let's put it somewhere on the side, 230 minus 29 divided by 5 parts, and because we want approximately similar temperature difference, similar heating up per each feedwater heater, and we get that the value by which we want to heat up our water is about 40 degrees C. So from this we will specify that the temperature at the point 3 outlet of the first feedwater heater will be this 29 plus 40. It's basically a new parameter, new boundary conditions. Same goes for the outlet of the second feedwater heater. We will add again 40. We have 109. Outlet of the Deaerator, point number 5. If we add another 40, so we would eventually miss 1 degree C. Here, to have nice round numbers, let's add 41, so that we have 150. Then we have the pump, point number 7, 150 plus 40 is 190, and 190 plus 40 is 230. Now we can have this temperature, 150 degrees C, is the temperature at which we are making our deaerator, and at the outlet of the deaerator the working fluid is at point of saturated liquid, so the quality is 0. And from quality and temperature we can get, similar as for the condensate outlet, we can get pressure. So we want to put in, we can leave this temperature, just saturated temperature is same as the temperature itself. and quality is here specified. And we can see that the pressure is a little bit less than 5 bars, about 5 atmospheres. And this is the pressure that, assuming no pressure drops in the water line, is same everywhere downstream down to the pump. So now we can continue calculating the state number 2. First isentropic, we have pressure, we have entropy. Enthalpy will be function of these two thermodynamic parameters. So let's help ourselves with previous functions. Previously written function. So we want enthalpy based on pressure, which we have here, and entropy, which is here multiplied by 1000 to get joules per kilogram and Kelvin. So here we get isentropic enthalpy and actual enthalpy. Same principle as last time. It's the enthalpy before the pump plus enthalpy difference divided by isentropic efficiency of the pump. Now state 2, we have enthalpy, we have pressure, we can calculate temperature based on this. So let's use we want to calculate temperature based on pressure and based on enthalpy, where the enthalpy is I4 times 1000 and it's temperature, so minus 273.15 to get temperature in degrees C. We can see that as the pressure difference is not very high, so also the heating up on the pump, the heating up of the working fluid on the pump is not very high. Now we can go further, where points number 3 and also points number 4 are points in subcooled liquid. So for the enthalpy, we will use function of pressure and temperature. Same goes here. And lastly, for the feedwater heater, we cannot use pressure and temperature, but we will use temperature on which we had specified a saturated temperature, and quality, which is 0. So here we also need to specify the entropy because it's the inlet of the pump. So it's basically the same function as here, or similar, because we will need the we will need the quality to be 0, so let's use just this function and change the output from enthalpy to entropy. Now for the isentropic change, the entropy stays, but we need the pressure. Again, we have specified pressure at the turbine inlet, and we have specified pressure loss of the boiler. So we will use the value of the pressure at the outlet of the boiler and divide it by, where do we have it? Divided by 1 minus pressure drop, and we get at roughly 13 megapascals. For the calculation purposes, we don't assume any further pressure losses downstream of the boiler. So now we get the pressure. We got pressure, enthalpy, its calculation of the pump, same as we did before. We can actually use the very same function to get the isentropic enthalpy, and then very same function to get the actual enthalpy. Just in the enthalpy function, we need to keep the isentropic efficiency of the pump. So we have pressure, we have enthalpy, we can get temperature to see how much we heat up our working fluid in the pump. Next, point number 7 and point number 8, again we have specified, and also point number 9. All of them are in single phase, so we can use this function for enthalpy in single phase, which we already did before, and we get further enthalpies. Now point 9 is a D-turbine inlet, single phase. We can use single phase function for entropy that we had before. Then isentropic entropy stays, and the pressure at point 10 is same as pressure at point 1. 5 kilopascals. So we have pressure, we have entropy, same thing that we did with the pumps, get the isentropic enthalpy, from this pressure, from this entropy, and since it's the turbine, so the enthalpy needs to the enthalpy at the turbine outlet will be lower than the ideal enthalpy, will be higher than the ideal enthalpy, because the enthalpy difference will be lowered due to the efficiency. So enthalpy at the inlet, enthalpy 9 minus enthalpy difference multiplied by isentropic efficiency of the turbine. Okay, now for the temperature at point 10, we use the same function using pressure and enthalpy as we did, for example, for the point 2. And we can use similar function to get also the quality of the steam at the outlet. we will want quality as a function of pressure and enthalpy. So we have the steam quality at the turbine outlet, and now we can move on to the feedwater heaters. So first, point 11 isentropic is same as entropy. Entropy is the same as entropy in the note number 9, which is actually also case for all the isentropic points during the expansion. So here we have also 13 isentropic, 15 isentropic, 16 isentropic, and number 18 isentropic. Now, in order to continue with the calculation, we need to understand the QT diagram of the feedwater heater heat exchangers. So here we have example of a QT diagram where we can see that the inlet steam can be in superheated state, or as we have seen before, it can be also in condition of wet steam. And we will assume that the minimum temperature difference is between the feedwater outlet and the condensing steam. We will assume a counterflow heat exchanger type, where on the other side of the heat exchanger there will be the minimum temperature difference between the inlet and between the inlet of the feedwater and the outlet of the subcooled condensate. So the condensate will not leave exactly at the saturated liquid point, but there will be certain subcooling. In our calculation, it means that if we know temperature at the point 8, so the temperature at the point 11 at the inlet of the feedwater heater, the saturated temperature will need to be higher by the minimum temperature difference. So point 11 feedwater heater is has the saturated temperature as temperature 8 plus delta T minimum for the high pressure part of the cycle. So we have saturated temperature at the point 11, and respective to that we can get pressure. Same function as we already had before. Using only saturated temperature as the parameter, and then the quality anywhere between 0 and 1. Then we said that we have pressure drop across the steam bleeding line. That means point 11 BL will be at higher pressure. And this drop in the pressure was considered to be corresponding to 2 degrees Kelvin at the saturated temperature. So the saturated temperature at 11 BL will be 2 degrees higher. And again, we can get pressure from that. Now at the point 11 isentropic, the pressure is same as point 11 bleed. It's just ideal and real outlet of the part of the turbine section. And now at point 11 isentropic, we have temperature, and this enthalpy is incorrect. We should have here constant entropy, and I can see that I did the same mistake all over my sheet, so sorry for that. So of course we have constant entropies. Now point 11 IS, we have pressure, and we have this entropy from the point 9, and based on pressure and entropy we can obtain enthalpy. So we have enthalpy after the ideal expansion, and now the real expansion is handled same as the expansion in the entire turbine. We assume constant isentropic efficiency across the turbine. So we can actually use the equation from the point 10, and we will just need to manipulate some variables a bit because the turbine inlet is still 0.9. So enthalpy at 0.9 minus enthalpy difference 0.9 and 0.11 is multiplied by isentropic efficiency. So we get value a little bit higher than for the ideal expansion, and now we have pressure, we have enthalpy, we can get temperature. And actually here we can see that the steam is really highly superheated, because here we have 380 degrees C while condensing temperature is just 240. Now to get our steam from state 11BL to 11 feedwater heater, so we have pressure drop. In real life there might be some heat loss, but we will assume insulated system where we have no heat losses, so throttling is isenthalpic process, enthalpy stays the same. Now state 11, we have pressure, we have enthalpy. We can again use functions of pressure and enthalpy to get other parameters. So function for the temperature will be the same as from previous. You can see that the temperature dropped a little bit, and we can see that it's really superheated. So using pressure and enthalpy to get the quality, we get -1, which is the indication of superheated fluid. Now the point number 2, if you remember the QT diagram, so we also had minimum temperature difference between the condensate outlet and the feedwater inlet. So here we are in subcooled state. The saturated temperature still stays the same, so does the pressure. But the temperature will be temperature at 0.7 plus minimum temperature difference for the high pressure part of the cycle. We have pressure, we have temperature, we can get enthalpy as function of these two. So for example it was at state number 9, same function that we want. And we get the enthalpy. So same principle as we did for the first bleeding stream will also take place also for the second one. So state 13 at feedwater heating inlet, we want temperature 190 degrees C, which is the required outlet temperature at 0.7 plus minimum temperature difference 5. Then accounting for the pressure loss in the way we do, for the turbine bleed we need to take saturated temperature respective to 2 degrees higher temperature, so we have 2 degrees higher temperature. Then we can use basically same function for the pressures as we did before. (11) isentropic is same pressure as 11 bleeding. Now we have the pressure, we have the entropy for the constant constant entropy change, so enthalpy is function of these two. That's what's here. For the 11 bleed, we can actually, and for future use, we can lock our state at point number 9. And we can use the same function for the enthalpy of the turbine bleed. Between the 13 BL and 13 feedwater heater, the enthalpy stays constant, and we can get the functions of temperatures from pressures and enthalpies in here. So we can see, we can confirm it also specifically by calculating the quality that we are still in superheated fluid, superheated gas. And the point number 14, it's at the same pressure as 13 feedwater heater, meaning saturated temperature is still the same, but actual temperature will be again following the QT diagram that we want. That means it will be temperature at point number 6 plus minimum temperature difference. And from pressure and temperature we can again obtain our enthalpy. At the Deaerator, the situation is a little bit different because it's a mixing heat exchanger. There is no temperature difference. So the point 15 feedwater heater, the saturated temperature is same as the temperature at the point 5. Because it's just mixing heat, basically a mixing tank. So saturated temperature of 150 degrees C. The turbine bleed temperature, saturated temperature again needs to be higher so that we get higher pressure at the turbine for the turbine bleed. Use the functions for obtaining pressure from saturated temperature. Now, point 15 isentropic, we have pressure, we have entropy. Use these two to get enthalpy. Now for the actual enthalpy, again we consider constant isentropic efficiency across the turbine, so we have the function ready. And during throttling, during pressure drop, when the system is insulated, the enthalpy stays constant. We can add the temperatures. And we see that still we are also in the turbine outlet with the turbine bleed at the superheated state. Following point is 16 isentropic, so we are going into the flowing into the low pressure feedwater heaters. So again we need to get the temperature of the saturation, which is here temperature at 0.4, 109, plus, and temperature difference at the low pressure part of the cycle. Sorry, it was at feedwater heater. Now at the bleed, the saturated temperature is 3 kelvins higher. Again we get pressures. Now from the pressure and entropy we get enthalpy. We get actual enthalpy, accounting for the turbine efficiency. And between BL and feedwater heater inlet there is no change in enthalpy as the system is insulated. At temperatures, and we can actually see that we would be already in two-phase in the wet steam, which is true. Point number 17, saturated temperature, also pressure stays the same. However, the temperature to follow our QT diagram that we wanted will be temperature at 0.3 plus minimum temperature difference at low pressure part of the cycle. We get pressure, we get temperature. From these two we can get enthalpy. And we are moving towards the last feedwater heater at 18. So here should be WH. So 18 feedwater heater. The temperature, saturated temperature should be point number 3 plus minimum temperature difference, which is 3 Kelvin. Here we have 2 degrees on saturated temperature for pressure losses. So we got temperatures. From saturated temperatures we get pressures. Now from pressure and entropy we get enthalpy. And we get following enthalpies. Just checking if the equations are correct. And get the temperatures and qualities. case. Now point number 19, cascading into the condenser. Pressure stays the same. Temperature, to get the Qt diagram that we wanted, so it's temperature at point number 9 plus minimum temperature difference. And from these two parameters we get enthalpy. So by this we successfully calculated enthalpies in all nodes of our cycle. Okay, now we need to figure out the mass flows at different nodes of our cycle. So we will again take a reference at point number 8, which will be mass flow rate of 1. And for the first feedwater heater, denoted here by lowercase a, we will have the following energy equation. The input of the feedwater heater is node number 7 and node 11 of feedwater side. So we will write H7 plus alpha A, the mass flow rate ratio for the feedwater heater A, times H11 FWH. Those were inputs, and now outputs. We have H7 plus our alpha A times the enthalpy at the point 12, H12. And from this we can get that the alpha H is fraction where we have H8 minus H7 divided by H11 FWH minus H12. Similarly with the feedwater heater B, the inputs are enthalpy H6, again with mass flow rate 1. As I said, mass flow rate in node number 8 is referenced as 1. So H6 plus our turbine bleed steam, so alpha B times enthalpy H 13 FWH and we have also the cascading input from the previous feedwater heater, so that's alpha A times enthalpy H12. And the outlets of this feedwater heater are enthalpy 7 multiplied by the mass flow rate of 1 and our node number 14 where the mass flow rate is alpha A plus alpha B times enthalpy at this node H14. So manipulating the variables, we get alpha B times H13 at feedwater heater minus H14 equals H7 minus H6 and now plus alpha A times H14 minus H12, and from this we can get alpha B as the ratio of this part divided by this one. Now we move on to the Deaerator. So the inlets to the Deaerator are node number 4, node number 15 feedwater heater, and node number 14. So the mass flow rate at the node number 4 is actually not the one which we have here, but the one less the mass flow rates of these three feedwater heaters, feedwater heating, bleeding steam, 11, 13 and 15. So actually the mass flow rate for the node number 4 is 1 minus and alpha A minus alpha B minus alpha C, and since it's energy equation, so multiplied by enthalpy H4, that's the one inlet. The other inlet is alpha C multiplied by H15 FWH, and the last input, node number 14, stream number 14, which is alpha A plus alpha B, the mass flow rate combined this one and this one, outlet is here, so alpha A plus alpha B multiplied by enthalpy H14. So these were the three inlets, and we have only one outlet where the mass flow rate is already 1. It's the same mass flow rate as we had here in the stream number 8, so minus H5, and this equals 0. Oh, and I forgot also, of course, this equals 0 and this equals 0. So now, after manipulating variables, we get (1 minus alpha A minus alpha B) multiplied by H4 plus alpha A plus alpha B multiplied by H14 and minus H5 equals our alpha C multiplied by H4 minus H15 feedwater heater from which we can get that the alpha C is a fraction where we have this member divided by this one. Okay, moving on to the feedwater heater D. So as we have seen already in the Deaerator, in the feedwater streams, the mass flow rate is 1 minus alpha A, alpha B and alpha C. So this mass flow rate multiplied by enthalpy H3 plus other inlet is alpha D multiplied by enthalpy H16 FWH. So these were inlets, and outlets are the mass flow rate in the feedwater stream multiplied by enthalpy H4 and alpha D here, going here, multiplied by enthalpy H17. So after manipulating variables, we get alpha D equals and now 1 minus alpha A, alpha B, alpha C multiplied by H4 minus H3 and divided by here H16 feedwater heater minus H17. And going to the last feedwater heater E. So the mass flow rate at the feedwater stream is again the same, 1 minus alpha A, alpha B and alpha C, and the inlet is enthalpy 2 and the other inlet turbine bleed steam is alpha E multiplied by enthalpy H18 WH, and we have another inlet, stream number 17, so there the mass flow rate is alpha D times H17. And we have two outlets, one at the feedwater side, so mass flow rate of feedwater multiplied by enthalpy H3, and the other outlet is stream number 19, where the mass flow rate is alpha D plus alpha E, and the enthalpy is H19. Now, after manipulating of the variables, we get alpha E equals and now again it's fraction, where on the top we've got 1 minus alpha A, alpha B, alpha C times H3 minus H2 plus alpha D times H19 minus H17, and in the bottom we've got H18 feedwater heater minus H19. So now we can implement our equations for the bleed steam mass flow rates into our file. So we have the reference mass flow rate here at point number 8, and at point number 11 we will have the alpha A, so it's H8 minus H7 divided by H11 feedwater heater minus H12. For the point number 13 we have H7 minus H6 plus alpha A times H14 minus H12 divided by H13 feedwater heater minus H14. Point 15 alpha C, so we have 1 minus alpha A minus alpha B multiplied by H4 plus alpha A plus alpha B multiplied by H14 and minus H5, and all this divided by H4 minus H15 feedwater heater. alpha D at point 16, we have 1 minus alpha A, alpha B, alpha C multiplied by H4 minus H3 and divided by H16 feedwater heater minus H17. And lastly, we have 1 minus alpha A, alpha B, alpha C multiplied by H3 minus H2 plus alpha D times H19 minus H17 and all this divided by H18 feedwater heater minus H19. So now we got the mass flow rates of our bleed streams, and we can also add mass flow rates in certain parts of the turbine. So at the outlet of the turbine, point number 10, if we look at the process flow diagram, which is here, so at number 10 our mass flow rate is 1 minus sum of all the bleed streams and we can actually see that at the end of the turbine we have only roughly 70% of the original mass flow rate entering the turbine. Now we can fill the mass flow rates of the remaining nodes in the cycle. So we can see that node number 9 is same as node number 8. Same goes for node number 8, node number 7, node number 6, node number 5. This is 6 and node number 5. Then at the node number 4, 3, 2 and 1, as we used also in our previous calculation, so it's 1 minus, or it's this 1 minus, and now these three streams of turbine bleed, so alpha A, alpha B and alpha C. And sorry, alpha A, B, C is these 11, 13 and 15. And this is the mass flow rate that is also on the remaining downstream points up to the point number 1. Now we have the mass flow rate in 10. Mass flow rate in 11 is in all points the same. Mass flow rate in number 12 is same as mass flow rate in 11. Mass flow rate in 13 is the leading stream. Just here we have, what do we got here? We have to use here little different formulation. 11 is number 10 is 1 minus alpha A minus alpha B minus alpha C minus alpha D and alpha E. So now point number 13. Point number 14 is sum of 12 and 13, so 13 plus 12. Number 15 is the turbine bleed. Number 16 is also the turbine bleed. Number 17 as well. Number 18 as well. And number 19 is turbine bleed from stream 18 and 17, the condensate. Once we have this, we will need to now, for calculation of power output, what's the mass flow rate in different parts of the turbine. So here we will prepare a small table and we split the turbine into the sections according to the feedwater heaters A to F. So in the point or part A, the mass flow rate is 1. In the part B, the mass flow rate is 1 minus alpha A. In the following part C is the previous one minus alpha B, so minus here point. So point B minus mass flow rate of point 13. D is C minus mass flow rate in 15. E is D minus mass flow rate in 16. D minus mass flow rate 16. And F is E minus mass flow rate in 18. Now we will put together into this table, just for clarity, inlet and outlet enthalpies of these sections. So the section A has the inlet enthalpy from point 9 and outlet enthalpy from point 11 bleed. Point B starts at this 11 bleed and outlet is 13 bleed. Following one starts at 13 bleed and outlet is at 15 bleed. Then another starts 15 bleed and outlet is at 16 bleed. We have started 16 bleed and outlet at 18 bleed, and the last section has inlet of 18 bleed and outlet is node number 10. And now we can calculate the power output of each section of the turbine by multiplying the mass flow rate times difference in enthalpy inlet minus outlet. And summing these up, we get work power output per 1 kilogram per second of the working fluid in node number 8 or at turbine inlet. So this is the turbine power output. But this is the thermodynamic power, so we need to multiply this by efficiencies of mechanical efficiency and generator efficiency. Then for the pump, we have two pumps in the system. So the first pump operates between point 2 and 1, so its difference in enthalpy H2 minus H1, but multiplied by mass flow rate that we have in this stream, which is here approximately 0.08. And we have second pump, this was condensate pump, and we have feedwater pump between 0.6 and 5. So H6 minus H5 multiplied by mass flow rate that we have at this point, which is 1. And this is thermodynamic power. So now we need to divide the thermodynamic power by mechanical efficiency and motor efficiency to get our power input for the pumps. The heat input is still straightforward, it's just difference of enthalpies 9 and 8. The heat output of the condenser is difference of enthalpies 10 and 1. But multiplied by mass flow rate that we have here, and it's the mass flow rate for the stream number 10, so here. And we have another rejected heat, which is the heat rejected from stream number 19. So we actually need to add difference of enthalpies H19 minus H1 multiplied by mass flow rate in the stream number 19. And net power output is the turbine minus pump. Now we can get to efficiency of the cycle, which is net power output divided by heat input. Efficiency of the plant, which is efficiency of the cycle multiplied by efficiency of the boiler. Heat input to our plant is net power output divided by efficiency of our plant. Mass flow of fuel is heat input divided by lower heating value of the fuel, and mass flow rate of steam at 0.9. So we get that by dividing the power output in kilowatts divided by net power output in kilojoules per kilogram. So we get kilograms per second. And as you can see, so the efficiency of the cycle and also efficiency of the plant is larger than the efficiency in our first case. Here we have roughly 39% at the cycle and 33% at the plant, while in the previous problem we had 37 at the cycle and 31 for the entire plant.